is up everyone, welcome back to the Kritya AI Labs Tech Interview Series, the show where engineers grow, learn and get hired. I am Baalu, Senior Technical Architect at Kritya AI Labs, and today we have an episode that I have genuinely been looking forward to recording. We are talking to a 2-year AI engineer, and I want to be very specific about why that experience band is interesting. 2 years in AI engineering is not junior anymore. This person has shipped things, hit production failures, debugged retrieval pipelines at 2 in the morning, and made real architectural decisions. But 2 years is also not so senior that every answer becomes abstract. The stories are still fresh. The scars are still visible. Our guest today is Saketh. He has spent the last 2 years building RAG pipelines, LLM agents, and document Q&A systems, the kind of systems that millions of developers are now trying to build. And today we are going to pull back the curtain on what actually happens when those systems meet real users, real data, and real failure modes. We are going to talk about retrieval failures that had nothing to do with your chunks, security attacks that most RAG engineers have never thought about, why testing an LLM application is philosophically broken, and the distributed systems problem that is hiding inside every vector index you have ever built. This is going to be a dense one. Grab your coffee, let us get into it. Saketh, welcome to the show.
Thank you, Baalu. Really excited to be here. I have been listening to this series for a while, so it feels a little surreal to be on the other side of the mic.
That is always a good sign. Means you know what you are walking into. Alright, let me start with something that is not on any standard interview prep list. I want to understand your journey not as a resume summary, but as a sequence of mental model upgrades. Most engineers who transition into AI engineering come from somewhere back-end, data science, research, whatever. And there is usually a moment, maybe 2 or 3 months in, where you realize the mental models from your previous world are actively misleading you in this new world. What was yours? What did you believe coming in that turned out to be wrong in a way that actually cost you time or cost a real failure?
That is such a good framing. So I came from back-end engineering. I spent about a year and a half before this building REST APIs and data pipelines in Python, and the mental model I brought in, the one that really cost me, was determinism as a baseline assumption. In backend engineering, if you write a function and you test it and it passes, you have confidence, same input, same output always, you build on that foundation, your entire testing pyramid is built on that assumption. When I started building my first large system, I carried that assumption with me. I wrote a retrieval function, I tested it with a few queries, it returned the right chunks, I moved on. I thought I had tested it, but what I had actually done was verify it worked for those specific queries on that specific day with that specific model version. 2 weeks later, nothing changed in my code, but OpenAI silently updated an embedding model. It was a minor version bump that they announced in a changelog that I was not watching, and my retrieval quality degraded noticeably on edge case queries. I did not catch it for 4 days because I had no monitoring. I was still mentally in the world where if the code did not change, the behavior did not change. The mental model shift that had to happen was understanding that in LLM applications, your dependencies are not just libraries with semantic versioning. Your dependencies are models, and models can change their behavior without a version number you can pin. That realization cascaded into how I think about monitoring, testing, and even system architecture. Everything downstream of that moment was different because of it.
That is a really honest answer, and I think it is more common than people admit. The silent model update problem is something I have seen trip up engineers who are genuinely good, and you touched on monitoring. We will come back to that. Let me ask you the second warm-up question, and it is very specific. You had worked with both OpenAI and Anthropic APIs. Most conversations about the two providers turn into a capability debate. Which model is smarter? Which benchmark score is higher? I want to go the other direction entirely. Tell me about the developer experience at the API and SDK level. Specifically, when you first integrated Claude into a system that was originally built for OpenAI, what is one concrete behavior difference in Claude? Not a quality difference, a behavioral or API contract difference that forced you to write code you were not expecting to write. Give me the actual code path that changed.
Okay, the most concrete one that I hit early was around system prompt handling and the way Claude enforces the separation between the system turn and the human turn. With OpenAI, I had gotten into a habit of doing something that a lot of engineers do. I was appending context and instructions dynamically into the messages array by adding assistant role messages before the first human message, essentially preloading the conversation with a synthetic exchange that set up context. It is a bit of a hack, but it worked reliably with GPT-4. The model would treat those synthetic exchanges as established context. When I ported that to Claude, the Anthropic API rejected it. Claude's API enforces a strict alternating turn structure. You cannot have two consecutive messages of the same role, and you cannot start the messages array with an assistant message. It is a hard API level constraint, not just a model preference. So I got a 400 error that I was not expecting, and I had to go back and refactor how I was constructing context. The code I had to write was a context packing function that consolidated all of that synthetic context into the system prompt instead of distributing it across fake conversation turns. That actually ended up being cleaner architecturally. The system prompt is where that stuff belongs, but it was a non-trivial refactor because my abstraction layer was assuming the messages array was the universal place to inject context. The other thing I had to write that I was not expecting was explicit handling for Claude's refusal format. OpenAI and Claude refuse in structurally different ways. OpenAI tends to give you a message that starts with something like "I cannot," and the response is still a valid text completion you can parse. Claude sometimes returns a more structured refusal that includes metadata in the stop reason. My response parcel was not handling that case, and I was surfacing raw refusal text to users for about a day before I caught it.
The context packing refactor. I have seen that exact pattern. Engineers end up with cleaner architecture because the API forced their hand, but the migration cost is real, and the refusal format difference is something that gets very little attention in documentation. Good concrete examples. Alright, let us move into the deep dive. Question 3, and this is where we start going deeper. When you built your document Q&A chatbot, I want to talk about a very specific failure class that is different from the usual chunking and embedding quality discussions. I want to talk about the query side of retrieval failure, not the index side. Here is the scenario. Your corpus is indexed correctly. Your chunks are well formed. Your embeddings are high quality. But users are asking questions in ways that cause the vector search to return chunks that are technically close in embedding space but semantically wrong for the actual intent of the question. The retrieval looks fine if you log it. You see chunks coming back. They are related to the topic, but the answer generated from those chunks is wrong or incomplete. When did you first hit this? What was the query that exposed it? And more importantly, how did you distinguish between a retrieval failure and a generation failure when the symptoms at the output level look identical?
This is something I hit around month 4 of running the chatbot in production, and diagnosing it took me longer than I am proud of. The specific query that exposed it was a user asking something like, "What changed in the refund policy?" The corpus had a document with the current refund policy and an older archived version of the policy. The query embedding for "what changed" was pulling in both versions, which makes sense. Both are semantically related to refund policy, but the generation model was synthesizing an answer that blended the two, sometimes surfacing old policy details as if they were current. Because from the model's perspective, it just saw two documents about refund policy, with nothing distinguishing their temporal relationship. The failure looked exactly like a generation failure at the surface. The model was saying something that was factually wrong about the current policy. My first instinct was to work on my generation prompt, add more instruction to be precise, be careful about contradictions. That did not help because I was treating a retrieval problem as a generation problem. The way I finally isolated it was by logging the full context window, every retrieved chunk with its metadata, alongside the generated answer, and then manually inspecting cases where users had flagged answers as wrong. When I looked at the context, I could see the contradicting chunks sitting right next to each other. The generation model was not hallucinating, it was faithfully synthesizing contradictory information. The query-side fix was query expansion combined with metadata filtering. Instead of sending the raw user query to the vector index, I started adding a pre-retrieval step where I used the LLM to classify the query intent and extract temporal signals, words like changed, new, current, latest, and map those to metadata filters on document date or version. So now when a query contains temporal language, the retrieval step adds a filter for the most recent document version. The vector search is still doing semantic matching, but the metadata filter is constraining the candidate set. The 3 logging points I would put in today to catch this class of failure early. 1. Log every retrieved chunk with its full metadata and the cosine similarity score at query time. 2. Log a hash or fingerprint of the context window that went into the generation call, so you can replay it. 3. Log user feedback or implicit dissatisfaction signals, things like follow-up questions that indicate the previous answer was not satisfying, and correlate those back to the context fingerprint. That way you can retrospectively analyze which context compositions are associated with user dissatisfaction.
The temporal signal extraction as a pre-retrieval step that is clean, and the context fingerprinting idea for retrospective analysis is something I want to dig into later. But let me follow up on one thing first. You mentioned cosine similarity scores in the logs. After that failure, did your intuition about what a good similarity score looks like change? Because I think a lot of engineers develop a kind of false confidence from seeing high similarity scores and assuming that means the retrieval was correct.
Completely. High cosine similarity just means the query and the chunk are in similar regions of embedding space. It does not mean the chunk answers the query. I have seen a 0.91 similarity score on a chunk that was genuinely unhelpful for the question because the question was asking for a comparison and the chunk was about only one side of that comparison. The score told me the topic was right. It told me nothing about whether the informational need was met. What I started doing after that was treating similarity scores as a necessary but not sufficient signal. I stopped using them as a quality gate on their own. Instead, I introduced a lightweight reckoning step using a cross-encoder, specifically the Markov Mini LM-L642 model, which is small enough to run cheaply, that rescores the top k retrieved chunks on query document relevance rather than embedding proximity. The cross-encoder scores and the original similarity scores often disagree on rank order, and when they disagree, the cross-encoder is almost always closer to what a human would say is relevant. The similarity score gets you the candidates. The cross-encoder tells you which candidates actually answered the question.
The 4-layer defense is comprehensive, and I want to pin something you said: namespace isolation enforced at the database level, not the application level. That is a principle that comes straight from defense in-depth thinking in traditional security, and I think most AI engineers build namespace isolation as an application concern and then wonder why a bug created a breach. The database level enforcement point is worth writing down if you are listening to this. Let me go to question 5, and we are shifting to testing. This is a topic that makes a lot of AI engineers uncomfortable because the honest answer is usually not very flattering. Standard unit testing philosophy assumes that the same input produces the same output. LM systems violate that assumption in multiple ways. Non-determinism even at low temperatures, silent model version changes, context sensitivity, and behavior that degrades gradually rather than breaking clearly. I want to know what your actual testing strategy looked like for your AI email assistant. Not the ideal version, not what you would do if you had unlimited time, but what you actually shipped with. And I specifically want you to tell me Where that strategy has blind spots that you know about and are uncomfortable with, I want the honest version. The description of LLM is judged as a measurement instrument you cannot fully calibrate. That is one of the most precise articulations of why that pattern makes engineers nervous even when they use it. And the honesty about shipping with known gaps is something I genuinely appreciate, because most people in interviews will tell you about the ideal architecture, not the one they actually built under time pressure. Let me push on the silent model update detection problem. You said your Gordon dataset would only catch it if the affected cases were in your 200 examples. What would it take? What is the minimum viable monitoring system to give you reasonable confidence that you would detect a meaningful behavioral shift within 24 hours of it happening, without rebuilding your entire testing infrastructure?
Minimum viable 24-hour detection. I think the answer is two things working together. First, a continuous Hadoop evaluation pipeline. Every production query, after it gets a response, gets asynchronously scored by a set of lightweight classifiers, not LM-based classifiers because that adds cost and latency, simple rule-based and embedding-based classifiers that check for things like: does the response contain the expected structural markers? Is the response length within historical normal ranges for this query type? Does the response embedding cluster near the historical centroid for this query category? These are not perfect quality signals, but they are statistical signals, and when a model update changes behavior, multiple signals tend to shift together. That creates a detectable anomaly. Second, a metric dashboard with rolling baselines and alerting. Track those classifier scores as time series. Set alerts on statistical deviation from the rolling 7-day average. If the average response length for a query category drops by 20% overnight, that is worth waking someone up for, even if no individual response looks obviously wrong. The 24-hour detection window is achievable with that architecture because the shadow evaluation runs on every query, so you accumulate statistical signal quickly on any production system with reasonable traffic. The part I have not fully solved is low traffic systems where you do not have enough queries in a 24-hour window to get statistical significance. For those, you basically need a synthetic canary query set that you run on a schedule, 100 representative queries fired against the model every hour, and you monitor those rather than relying on organic traffic.
Canary query sets run on a schedule? That is actually a teen idea, and I have not heard it described that precisely before. Alright, question 6. This is a system design question, and I want you to put on your distributed systems hat. Your document Q&A system is live. Users are querying it constantly. Meanwhile, the underlying document corpus is not static. Documents are being added, existing documents are being revised with new content, and some documents are being deleted because they are no longer valid. The vector index has to reflect all of those changes, but re-embedding and re-indexing takes time. During that re-index is stale. I want you to design the consistency model for that system. Specifically, what staleness guarantees can you actually make and commit to, not aspirationally, but as an engineering contract? And then the harder question: when a user gets an answer that turns out to be based on content from a document that was revised 2 minutes ago, how do you communicate that to them in a way that does not destroy their trust in the entire system?
This is genuinely one of the hardest problems in production RJ, and it does not get talked about nearly enough. Let me start with what staleness guarantees you can actually make, because I think most engineers overclaim here. The honest guarantee you can offer is eventual consistency with a bounded staleness window. You cannot offer strong consistency in a system where re-embedding takes real time unless you are willing to take the index offline during updates, which is not acceptable for a user-facing product. What you can do is measure and publish your actual P95 update latency, the time from when a document is revised to when the new embeddings are queryable, and treat that as your SLA for index currency. In practice, on a system I built using Pinecone with an async reindexing pipeline, the P95 update latency was around 90 seconds for a document of normal size. That was the actual number. So the honest contract is, the index reflects the state of documents as of approximately 90 seconds ago under normal conditions and up to 10 minutes ago under high indexing load conditions. For the tombstone problem on deleted documents, I do not delete chunks immediately. I use a soft delete pattern where deleted documents get a metadata flag set to deleted equals true, and all queries include a filter that excludes deleted chunks. The actual chunk deletion from the index is deferred and happens in a batch cleanup job. This means deleted documents are immediately invisible to queries, but their chunks still exist physically in the index for up to an hour. The reason for this design is that immediate hard delete in vector databases is often slower and more operationally risky than a metadata filter, especially at scale. For revised documents, I use a versioning strategy. When a document is revised, I do not update the existing chunks, I insert new chunks with an incremented version number and a new timestamp, and I update the document registry to mark the old version as superseded. Queries filter for the latest version by default. This gives me the ability to roll back to a previous version if the new embedding batch is corrupted, which has happened. On the user communication question, this is where product and engineering have to collaborate, and most engineers throw it over the wall to product. My approach was to add a provenance timestamp to every answer, not a warning banner. Users ignored those, but a subtle inline citation that says something like based on documents as of and then a timestamp. If that timestamp is older than your tailness SLA, you show a small indicator that says the information may be updating. The key design decision was making this feel like a feature, like showing the user when information was last verified, rather than a disclaimer about system limitations. The same information framed as a feature versus a warning gets very different user reactions.
The provenance timestamp as a feature rather than a disclaimer, that is a UX insight wrapped inside a systems design answer. And I think that is exactly the right way to think about it. You also touched on Pinecone. Let me ask a quick follow-up before we move on. How does the consistency model change if you are on a self-hosted Chroma instance versus Pinecone serverless? Are the primitives meaningfully different, or is it basically the same problem with different operational overhead?
The primitives are different in ways that matter for this specific problem. Pinecone serverless gives you eventual consistency that is managed by Pinecone's infrastructure. Upserts are acknowledged when received, but queryable after an internal propagation step that you cannot control or observe directly. You can call their describe index stacks endpoint to check if our upsert has propagated, but it is polling, not a notification. Chroma self-hosted with the default settings is actually synchronous on writes. When an add or update call returns, those vectors are immediately queryable. That sounds better for consistency, but it comes with a cost. Light operations are blocking, which means if you are doing a large batch reindex, you are blocking the query path on the same instance unless you architect around it with separate read and write replicas, which adds significant operational complexity. So the consistency model is genuinely different. On Pinecone, you have eventual consistency with a non-observable propagation delay. On self-hosted Chroma, you have synchronous consistency with blocking write semantics. For a system where documents are updated frequently and users are querying simultaneously, Pinecone's model is actually more operationally manageable because writes never block reads. But you pay for that with the inability to guarantee that a write is immediately queryable, which means you need that staleness window monitoring I described earlier. The other meaningful difference is that Pinecone gives you transactional metadata updates that are cheaper than reupserting vectors. So the soft delete pattern with metadata flags is very cheap on Pinecone. On Chroma, metadata updates require a full document update which rewrites the vector as well, which is more expensive at scale.
Good, that is useful operationally then. Alright, question 7. This one is about NN algorithms, and most engineers treat vector databases as black boxes. I want to open the box a little. You have used both Pinecone and Chroma. Most production vector databases use HNSW, hierarchical navigable small volume graphs, as their AN index structure. The approximation in NN means that at query time, You are not guaranteed to get the true nearest neighbors. You are getting an approximate set that is close but not perfect. Most engineers never notice or care about this gap. Here is my question. Without looking anything up, walk me through your intuition for what the M parameter in HNSW actually controls, not the textbook definition, but what you think happens to your retrieval quality and your index build time if you double M from its default value. And then tell me at what scale of vectors you started caring about these configuration parameters versus treating defaults as sufficient.
Okay, my honest intuition on M, not the textbook answer. M in HNSW controls the number of bidirectional connections each node in the graph has to its neighbors. Think of each vector as a node in a graph, and M is how many edges it gets. A higher M means each node is connected to more neighbors, which means the graph traversal during query time has more paths available to find the true nearest neighbors. My intuition for what happens when you double M, your recall goes up, you retrieve the true nearest more accurately because the search path has more options to navigate through the graph and is less likely to get trapped in a local optimum. That is the good side. The bad sides are that your index takes longer to build because you are creating and managing more edges per node during construction. Your index takes more memory because those edges have to be stored, and your query latency may actually decrease slightly in some cases. This is counterintuitive, but a denser graph can sometimes find the answer faster because the paths are shorter. But for large M values, the memory overhead starts dominating and you get diminishing returns on recall. The other parameter worth mentioning is F as construction, that controls how many candidate nodes are examined during index construction. My intuition is that if as construction affects build time recall, how carefully the graph is constructed, and higher values give you a better graph at the cost of longer build time, while M affects the graph structure itself and has runtime implications. On when I started caring about these defaults, honestly not until I was in the range of 1,000,000 vectors or above. Below that threshold, the defaults on Chroma and Pinecone are conservative enough that the approximation error is negligible for most query workloads. Where I first noticed it was when I had a corpus with a lot of very similar documents, technical documentation, where many chunks had very high mutual similarity, and I was seeing cases where the top K results did not include a chunk that I could manually verify was more relevant than some of the returned results. I ran a brute force exact search against a sample of queries to establish a recall at 10 baseline, compared it to the ANN results, and found I was at about 92% recall. For that workload, bumping F adjustment improved recall to around 97% with a build time penalty I could absorb. The 5% difference in recall turned out to matter because it was systematically missing certain types of edge case queries.
The authoritative only true class concept, that is a design pattern that I have not heard named precisely before, but it is the right abstraction. You are essentially defining a trust hierarchy for your tools, where some tool categories are not allowed to fail gracefully into confabulation. That is important enough that I am going to say it again for anyone listening. Certain tool categories should be defined as authoritative only, meaning that if they fail, the agent surfaces the failure, it does not synthesize around it. That is a system design decision, not a prompt engineering decision. Alright, let us move into the war stories section. Question 8. This is the system design and cost engineering question, and it is about a problem that most teams only discover after their first unexpected billing shock. In a multi-tenant LM application, a single user request might touch 3 different LLM calls, 2 embedding calls, and a re-ranking call, all orchestrated by your agent or pipeline layer. At the end of the month, your OpenAI bill arrives and you know the total. What you do not know is which feature cost 30% of that bill, which user cohort is disproportionately expensive to serve, and whether the cost per successful answer has been going up or down as you have added features. Walk me through how you would design per feature cost attribution in that system. Not the ideal future state, the version you would actually build in a week that gives you useful signal. Specifically, how do you attach cost to the right feature and the right user without that instrumentation adding meaningful latency to the critical path?
I can tell you exactly how I built this because I had the billing shock experience and built the attribution system in response to it. The core insight is that token counting does not need to be on the critical path. Every LLM API response, OpenAI, Anthropic, both of them, includes usage metadata in the response payload. OpenAI gives you prompt answer tokens, completion answer tokens, and total answer tokens in the usage field of every response. Anthropic gives you equivalent data in the usage field of their response objects. This data is already there, you are not making an extra API call to get it. So, the instrumentation cost on the critical path is essentially zero for token counting. It is just parsing a field that is already in the response you received. The question is how you route that data to your attribution system without adding latency. The architecture I build, every LLM call in the system goes through a wrapper function that I called traced LLMs call. That function takes two extra parameters beyond what the underlying API takes, a feature or ID string that identifies which product feature triggered this call, and a session or context object that contains the user ID and rext or ID for the current request. When the API call completes, the wrapper function constructs a usage event feature underscore ID, user underscore ID, tenant underscore ID, request underscore ID, model, prompt underscore ID tokens, espinator underscore ID, timestamp, and publishes that event to an async queue. I used a simple release list as the queue in my implementation. The actual writing to a time series database happens in a background worker that consumes from that queue. None of this blocks the request thread. The estimated uncast as this the field is computed client-side using a price table that I hardcode and update manually when providers change pricing. It is not perfectly accurate pricing changes and I sometimes updates, but it is accurate enough for attribution purposes. The goal is not cent level accuracy, it is order of magnitude accuracy, so you can see that feature X costs 10 times more per request than feature Y. The answer to your question about what I found when I had attribution data, the first thing I discovered was that my document re-ranking step, which I thought was a minor quality enhancement, was responsible for about 18% of my total monthly spend because I was re-ranking the top 20 chunks every time, even for simple queries where top 3 would have been sufficient. I had never looked at the cost per call of the re-ranker because it was a third-party API and it was buried in a line item that I was not scrutinizing. Once I had per feature attribution, it took me about a week to add query complexity classification that skipped re-ranking for simple informational queries, and that dropped that 18% to about 6%. On the consistency model for async cost accounting, else you will have undercounting in failure scenarios where a response is received but the usage event fails to publish before a crash. I treat this as acceptable. The alternative, synchronous cost recording on the critical path, adds latency that I am not willing to pay for attribution data. Statistically, the undercounting rate is less than 0.1% in a reliable system, and it is randomly distributed, so it does not distort the feature level attribution ratios in meaningful ways.
The traced LLMs call wrap-up pattern with async event publishing is exactly the right architecture for this. And the re-ranker discovery, 18% of your bill from a step you were running unconditionally, is the kind of thing that you simply cannot see without per feature attribution. That is a story worth telling to any team that thinks their AI costs are just a function of request volume. Let me ask you a follow-up that connects the cost question to something operational. When you now have per feature cost data and you want to stitch together a trace that spans multiple LLM calls for a single user request, so you can see this one user request cost me $0.32 distributed across these 3 module calls. How do you propagate the request ID across asynchronous boundaries in your orchestration layer? What breaks when you try to do that? Context verb for async context propagation. That is a Python specific answer that shows you have actually debugged this in production. The LangChain callback integration for injecting trace context is genuinely non-obvious. Alright, let us go to the rapid fire round. I am going to ask you 6 short questions and I want direct, opinionated answers. No hedging, no it depends. If you genuinely believe it depends, tell me what it depends on in one sentence and then give me the answer for the most common case. Rapid fire question 1. Semantic caching. The idea of using embedding similarity to cache LLM responses so that semantically similar queries return a cached answer rather than hitting the model. Genuinely useful in production, or a clever idea that breaks more than it saves? Rapid fire question 2. Hybrid retrieval BM25 plus dense vectors combined via reciprocal rank fusion. Do the operational costs justify running both systems, or is dense only retrieval sufficient for most production workloads?
Justified for workloads with significant keyword-heavy queries, product codes, proper nouns, technical identifiers, anything where exact string matching matters. Dense retrieval genuinely fails on exact lookups because the embedding space does not preserve character-level specificity. If a user searches for a specific contract number or a specific error code, BM25 will find it and dense retrieval might miss it. The operational cost of running BM25 alongside dense retrieval is lower than it sounds because BM25 is computationally cheap. It is inverted index lookup, not neural inference. The hard part is the fusion and the infrastructure of maintaining two indexes in sync. For a document corpus that is mostly prose and conceptual content, dense only is fine. For anything with identifiers, codes, or named entities that matter for exact match, hybrid pays for itself.
Rapid fire question 3. Temperature 0. The common wisdom is use temperature 0 for any task that requires accuracy or consistency and use higher temperatures for creativity. Is that rule of thumb correct, or is it a dangerous oversimplification?
Dangerous oversimplification. Temperature 0 does not mean deterministic. It means the model always picks the highest probability token at each step, which produces the same output only if the computational path is identical, and that is not guaranteed across different hardware batching configurations or model versions. Engineers build false confidence around temperature 0. The deeper problem is that for agent planning tasks specifically, temperature 0 can make the agent brittle. Planning requires some exploration of solution paths, and temperature 0 locks the agent into its first plausible path even if that path leads to a dead end. I have seen agents at temperature 0 get stuck in tight retry loops because they keep generating the same failed plan deterministically. A small amount of temperature 0.1 or 0.2 adds just enough variance to escape those local optima. The rule I use now, temperature 0 for structured data extraction and format constraint tasks, 0.1 to 0.3 for planning and reasoning tasks, higher only for explicitly creative tasks.
Rapid fire question 4. Context window sizes keep growing. 128k tokens, 200k tokens, models that came to handle a million tokens. Does this make chunking and retrieval architectures obsolete, or is there still a fundamental reason to chunk even if you could technically fit everything in context?
Not obsolete, but the trade-offs shift. The lost in the middle problem is real and empirically demonstrated. LLM attention degrades on content in the middle of very long context, so stuffing 200k tokens into context does not mean the model uses all of it equally well. Chunking and retrieval let you put the most relevant content at the attention optimal positions in context, the beginning and the end, rather than hoping the model attends correctly to page 47 of a 300-page document. Beyond attention quality, there is the cost and latency argument. Processing 200k tokens per query is expensive and slow. If Retrieval can narrow it to 4k tokens of high relevance content, you get faster, cheaper answers that are often better because the relevant content is not diluted by irrelevant context. Long context windows are genuinely useful for tasks where document coherence matters. Analyzing a contract where you need relationships across the whole document, or reasoning over a long conversation history. For retrieval over a large corpus, chunking plus retrieval is still the right architecture. The two paradigms complement rather than compete.
Rapid fire. Final question. One thing in the AI engineering space right now that you think is being systematically underbuilt by the industry, not undervalued conceptually, but actually not being built well in most production systems you have seen or heard about. What is the thing that most teams are skipping?
Feedback loops with teeth. Everyone talks about RLHF at the research level, and everyone puts a thumbs up, thumbs down button in their UI. But almost no one has a system that closes the loop from that feedback signal back into an actual measurable change in system behavior within a reasonable time window. The thumbs down gets logged somewhere. Maybe someone looks at it in a dashboard once a week. Maybe it gets discussed in a team meeting. And then nothing changes until someone manually inspects the logs and decides to rewrite a prompt. That is not a feedback loop, it is a feedback archive. What teams need and almost none have is an automated pipeline that aggregates feedback signals, identifies query categories with statistically elevated negative feedback, generates candidate prompt improvements or retrieval configuration changes for those categories, tests those changes against a held-out evaluation set, and gauge deployment on measurable improvement. That pipeline does not require AGI to build. It is mostly data engineering and evaluation infrastructure, but it requires a team to prioritize it over building new features, and almost no one does until they are in a crisis.
Feedback loops with teeth. I love that framing. A feedback archive is not a feedback loop. That is quotable and it is true. Alright, let us bring it in for the wrap up. Saketh, this has been a genuinely rich conversation. I want to do two things before we close. First, I want to give you a chance to share one insight, something we did not cover, or something you want to underscore that you think is the single most underappreciated lesson from your first 2 years building production AI systems. Not the most technically impressive thing, but the thing that would have saved you the most time if someone had told you on day one.
The most underappreciated lesson, and this is something I had to learn the hard way multiple times, is that the prompt is not the architecture. When you are starting out, every problem feels like a prompt engineering problem. The model is returning bad output. Improve the prompt. The retrieval is not working well. Write a better system prompt to help the model use the context. The agent is making wrong decisions. Add more instructions to the prompt, and sometimes that works. But the class of problems that are actually architectural retrieval design, context budget management, tool schema design, state management, error propagation cannot be solved by better prompting. They require you to change what the system does, not just change the instructions you give the model. The engineers I have seen stagnate the most in their first year are the ones who become very sophisticated prompt engineers without building strong architectural judgment. They can write beautiful prompts that expect perfect behavior from a model in a notebook demo, and then cannot figure out why the same approach fails in production under load with real user data and with tool calling in the mix. The architecture is not in the prompt, the architecture is in the code around the prompt. If I had to give one piece of advice to someone starting out, spend 20% of your time getting good at prompting and 80% of your time building the infrastructure that makes prompting a small part of the overall system quality equation.
The prompt is not their architecture. Print that on a t-shirt. Seriously? That is the kind of insight that sounds simple when you say it, and yet is genuinely hard one when you have seen the failure mode it is addressing. Saketh, thank you for being honest about the failures, the things you shipped knowing they had gaps, the security threats you did not model until you did, and the testing strategies that were pragmatic rather than perfect. That kind of honesty is rare in technical conversations, and it makes the whole thing more useful for everyone listening. It has been a genuine pleasure.
This was exactly the kind of conversion I hoped it would be. The questions forced me to think through things I had not articulated clearly before, which is the best outcome you can ask for from an interview. You learn something about what you know by trying to explain it.